It's great to be here. Thank you so much for having me, Ken and Marie, and the rest of the team from the Center on Longevity. And I was spending a few minutes last week and talking with the team today about the incredible projects that our design teams will be presenting on today. And I can see you're all excited, a little nervous, but I think you're in a room full of fantastic supporters and champions that stand ready to help you to bring these projects to life and maybe bring them to great real world products like we saw in that introductory video. So it's also great to be on the 10th year of the Stanford Center of Longevity contest here. And I'm very honored to be selected for that position. So I'm a professor of mechanical engineering here at Stanford, and I direct the Stanford Biomechatronics laboratory. And we're focused on a very specific way of trying to improve quality of life and to lengthen life by increasing physical activity. And in particular, we are trying to make walking easier for people who are experiencing mobility loss, either as a result of aging or from disability, or for people who simply face challenges in mobility because of the arduous conditions under which they walk in their jobs or lives, like these aid workers in rural Africa. And the way that we're trying to do this is by giving people robots that they can wear on their legs that make walking easier for them. And we call those exoskeletons, in the case of a device that you wear outside your limb, and prosthetic devices for people who've limb loss. And I come at this from the perspective of a roboticist. Speaking of longevity, this is one of my first projects. This is me about 1,000 years ago as an undergraduate student at Cornell University. And the way I got excited about this kind of research is through walking robots. This is a passive dynamic walking robot that is just a set of sticks and hinges, no motors, computers. But when you give it the right initial conditions, it has this motion a lot like human walking. And then a second robot we created was to add minimal power to this device, kind of like adding a motor to a glider, to create a really energy efficient walking robot. And this machine held, and I think it's still tied for the cost of transport record for walking robots. So when I became a PhD student, I wanted to take some of these technologies that worked so well at enhancing efficiency for legged robots to try to fight the fatigue that accompanies aging and disability. People have elevated energy costs to go the same distance. So maybe we could use those same techniques for prosthetic limbs and exoskeletons. But what I found was that this is a lot harder than it seems. This is the popular image, right, of the exoskeleton designer and Tony Stark here. For him, it's all about this fancy new energy supply and clever mechanical design, or just having a big budget. And, I'm a clever mechanical designer. I thought maybe, this is going to work out great. But it turns out none of those things address the real problem. And if you take one thing away from this presentation, I want it to be this. The real problem in designing devices like this is that humans are very complex, highly complex in our bodies, and especially in our nervous system. And that complexity means it is very difficult to predict how a person will respond to some new device that you give them. I'm sure you've all run into this in your design challenges when you first interact with your potential users. Sometimes it doesn't go the way that you expected, right? And that's a super important part of the design process. The same thing applies for these robotic devices, even though they're doing something physical and there's physics and energy and speed and so on. Really, the key is, how does the person adapt to it? And so this is a really slowed down progress in my field. In the bad old days, the way we've done this is we'd dream up a device, we'd build it, and then we test it on people. And because we didn't have a good model of people, it wouldn't help them. And that process takes years. It's really hard to make these physical devices and have them function as intended. And then, of course, the PhD student would graduate and you start over. And the faculty in the room know what I'm talking about. So for years, we've been promoting ways of making this empirical approach go faster. And in particular, we're suggesting using a couple of tools. And the first is something we call universal device emulators. The idea here is that we're going to leverage the laboratory setting. So you can see this is a person wearing an exoskeleton that's tethered to big, powerful motors and computers that you couldn't put on their body. And that means that the system can be really versatile. Instead of being product-like, it's a very versatile test bed. And you can think of this as sort of a virtual reality system for your legs. The person has the physical experience of interacting with some device without you having the overhead of designing and building it. And that means we can test new ideas for assistance in days or even minutes rather than years. So that's one way to speed the process. We're still faced with this challenge that there's this vast space of possible designs that we need to test. So the second set of tools we developed, we call algorithms for human-in-the-loop optimization. And this is a complicated looking slide and it's a sort of a jargony word, but all that means is we give a person a device and they wear this exoskeleton emulator, and then the device renders some virtual product to them, and then they walk, or in this case, running, while the assistance is applied. And we measure their real performance. In this case, we're measuring metabolic rate. This is, they have that mask on. We can measure the oxygen their body is consuming and use that to estimate the biochemical energy that their body's using up, which is an indicator of fatigue. And after a little while, the device changes its behavior and we measure performance again. And we do that over and over again for a few hours. And slowly the system identifies the very best set of characteristics for them that maximizes their performance. And this is really effective. So I'm going to start sort of farthest away from our target population and get closer and closer over the course of the presentation. So during running, we find that we can reduce the energy cost of running by about 25% compared to wearing the device when it doesn't apply any assistance. So that the benefit of turning it on is about 25%. There's still this big cost of putting this versatile test bed on because it's heavy and can fit lots of different people and stuff like that. But focusing on that benefit of assistance, about 25%. And we've applied this approach in lots of different contexts. So for instance, trying to reduce the energy cost of walking at a typical speed, 1.25 meters per second here, or trying to increase people's self-selected speed. So this participant's walking on a self-paced treadmill where you choose how fast you want to walk and the treadmill just matches you. And in both of those cases, with just assistance at the ankle joint, we found that we can improve speed and energy economy by about 40% compared to wearing the device inactive. And we've done this with a wide variety of devices. I'll just show you one more example. This is a hip, knee, ankle exoskeleton. And here we have someone walking at a fast speed. Here they're walking with this very heavy weight vest. And then we're walking uphill at a pretty steep grade. And in all of those conditions, we find we can use emulation and optimization to identify really effective assistance techniques and have the energy consumed by the person. So that's all, very cool, but it's all in a laboratory setting. How are we going to get these devices out to people that need them and they can use them in the real world? The design approach here is that once we have solved the truly hard problem of figuring out what people need, then we have design blueprints for a product-like specialized device that we can make. And that's actually my favorite part. That's what attracted me to this problem. I think a lot of the roboticists and mechanical engineers who do this are excited about that hardware design part. So here's a video of our latest device. And this is an untethered ankle exoskeleton that is based on the results of our laboratory trials. And I'm going to spend a little bit more time on this study because it came out recently. We're very excited about it. We think it has some translational potential. And this was a collaboration, typical Stanford style. We had this fantastic PhD student, Patrick Slade. He's starting as a professor at Harvard in the fall, and he was co-advised by a few people, Scott Delp in bioengineering, Michael Kokendorfer in AirAstro, and myself. And we wanted to take it a step further in this project, not just make a static device that goes out into the world, but also have that device individualize assistance to people while they walked around in the real world. And this is probably the hardware that you've seen, for those of you who have seen exoskeletons walking around campus. This is probably the piece of hardware. And the first challenge we had to face was, how do we optimize assistance without access to all that fancy lab equipment, right? We don't have that metabolics mask, for example, that measures your energy consumption. And the way we overcame that was by developing this new data-driven approach to optimization. So we used all of the data that we had collected in the laboratory, and we trained a model that used only sensors on the exoskeleton. So it just used the joint angle and velocity and how much torque the exoskeleton was applying. And from that information alone, it could infer which of two conditions was better, which one resulted in lower energy cost for the user. And that was enough to perform optimization. And we tested this against the laboratory-based method. Here you can see over here's the energy cost, lower is better. And this green box is for the lab-based, and the blue box is for our data-driven method. They come out about the same improvement. And that's very exciting. It means that people's movements encode information about important biochemical outcomes inside the body, which is very cool. And you can leverage that to individualize the device assistance and to maximize performance for the user. Another kind of fun thing is that the optimization the data-driven approach converged about 4 times faster, because the information that we were taking from the person is this movement data rather than physiological information that has long delays associated with the expression of oxygen and carbon dioxide in the expired gases. Now, one of the things you worry about when you train a model is overfitting to the training data. And if you use ML AI techniques in your work, this is something to be very careful about. So we wanted to make sure this would generalize to a meaningful set of conditions. So we trained on data only from a normal walking speed. And I was frankly a bit surprised, but this generalized well to very slow walking, about 0.75 meters per second, up to quite fast walking, 1.75, and walking on a steep incline. And you can see the bars are about the same, and the torque pattern that the optimizer identified was about the same for both of those methods across this range of conditions. So the last thing that we worry about here is, most device experiments are conducted on a treadmill in a laboratory, and the person walks at a steady speed for a long time. That's not how people walk in the real world. People in the real world take lots of short bouts of walking at a wide range of speeds. So we wanted to make sure this would apply in those conditions. And so we developed a way to sort of collect little bits of data while people walked in natural ways, and we could accumulate enough data over an hour or so of walking to perform this optimization we needed. And to get people to change speeds, what we did is we gave them these fun, ecologically valid prompts, which I can see from your faces that you've read a few, like walk like you're walking a small dog, or like you've had a bad day, or like you're late to class. And that then we verified that resulted in a typical distribution of speed and of the duration of the bouts of walking. Finally, we tested whether the assistance that we identified was effective by having people walk this course outside on the Stanford campus. And we tested 3 conditions. One was optimized assistance. One was this generic assistance, which was sort of our best guess based on all prior data as to what would be effective. And finally, normal street shoes that people walked in on. And what we found is that optimized assistance improved the energy cost of transport. That's how much energy you used to get from point A to point B by almost 20% compared to normal street shoes. So now we're accounting for all the added mass of the device and everything. And that's a big improvement. That's about double what is considered to be a clinically relevant improvement in energy cost that to affect things like fatigue in daily life. And we found that people self-selected a speed that was about 10% faster, which is really important. This is a key outcome for many groups are trying to assess. And that you also see that optimized assistance is better than the generic assistance. And that tells us that individualizing the behavior of the device to each person's needs was an important feature for this. We then took that same device and pattern assistance and applied it in the treadmill settings that most people used, so we could compare to past exoskeletons, and found we can improve these outcomes about twice as much. These are the blue dots are from this study, as any prior exoskeleton study. We're also working on extending these approaches to several populations, including people with amputation. So here's a device that has 3 independently actuated digits. And you can see this person's walking on an uneven treadmill, which is intended to challenge their balance. This is one of the most important outcomes for people with amputation. And what the device is doing is canceling out that uneven surface, so it feels like they're walking on a level surface with their prosthetic side. Candidly, this didn't have the benefits that we had hoped. Like, as I said at the beginning, most things we try are ineffective, but we are iterating through lots of new techniques very quickly with these systems, and sooner or later, we're going to find something that does benefit people with amputation. As I mentioned, a really important outcome for many of our populations is balance. And so we're doing things, and this is, every time I show this video, I notice my student is not wearing his harness, safety harness, and I think I need to talk with Michael about that. So we challenge people's balance, we measure their recovery response, and we use that to understand how good their balance is. And we artificially impair people in the lab to develop a metric, and we're working on exoskeleton control that helps people during that recovery. This is most common reason for older adults having a fall is unexpected changes in contact with the environment, including bumping things, say passing through a doorway or past the table or chair. And we're working on exoskeleton control that could jump up and assist them in those kinds of conditions. I've kept this pretty short so that we have lots of time to discuss. I would just want to acknowledge this work is done by a fantastic team of PhD students and postdocs in our group. I want to particularly note Patrick Slade, who's led our untethered exoskeleton work, and Abba Makmazaheri, who has led our work with older adults so far. And I'll just conclude by saying that here at Stanford, we're working to improve quality of life and to lengthen life by increasing physical activity, using an approach of smart, targeted design of wearable robotic devices, and applying the latest advances in robotics, data science, and bioengineering. And we're very glad to have you join our community. Thank you.
So I'll start, get the ball kicked off. So how would you see this work proceeding towards potential commercialization? What's that path look like for you?
It's a great question. So a couple of the technologies we developed in our lab have translated, and there are companies out there. So our emulators are now made by a company called Human Motion Technologies in Pittsburgh. And it's like a 5 to 10 person company. They sell these as research tools to other laboratories. The way that happened is my first PhD student developed the technology in our lab and wanted to start a company. And we sort of worked together to get that out the door, and then he's running the company. And I think that's a formula that works really well when you have this champion who's passionate about the application and deeply knowledgeable about the technology through their research in the lab. And there's another company like that. I haven't talked about this all today, but we developed this new kind of clutch based on electrostatic adhesion, kind of a different topic. But Stuart Diller, PhD student in our group, spun out a company. That company is now doing well. Same formula. So right now, what I'm looking for, I feel like this technology is ripe for commercialization. I think we've hit that minimum viable product level. But I'm a professor, And that takes a lot of my time. And I kind of like being a professor. I don't want to quit being a professor and be a startup president. So what I really need is a bright young person who's very excited and wants to make lots of money and anyways, change the world. Anyways, just, I'd say that's the process. Any other thoughts or questions?
Thank you. Yeah. So I noticed you started off like your robot has like hips, knees, ankles, all the joints, right? But in the end, it ended up being like the research is on like just the ankle joint. And I'm a PT, so I know like the more joints you cross, the more degrees of freedom, right? You got to control. So do you think there's going to be a point where there's going to be like ankle and knee or ankle, knee, hip, like exoskeletons or?
Yeah. Absolutely. Yeah. So I think that the first products that are really viable will be fairly minimal to make it easy to don and doff. So putting on and taking off the device, this is a critical barrier to overcome in a product like this. And we're learning from failures in some of the first products to go to market in this area. For example, very fancy upper extremity prostheses. Many people have purchased these and then they sit on a shelf in the closet, right? And there's a similar dynamic with powered ankle foot prostheses. And some of the critical issues are, first, you need a big improvement in functional outcomes. Like it has to really work. And that's something we've been focusing on. A second is that the inconvenience of using it has to be very low. So if the batteries run out after 30 minutes or an hour, which happens with those powered prosthetic feet, people won't use them because you feel like, oh, my battery might run out, and then I have this heavy thing that's not helping me that much. And similarly, putting things on and taking them off, that little activation energy, that little thing before you can get into the deeper potential well, we face that in all our lives, right? Getting started at if there's an extra step before you get on your bike to ride to work, you're way more likely to drive the car or something. So I think single joint devices are likely to be first, but of course, for different populations, different joints will be necessary, and I think we will see those. There isn't yet we've interacted with a few big companies that are excited about billion-dollar markets and things like that, and we still haven't seen an example of a wearable robotic technology that's reached that level of success. So what we really need right now is somebody to launch a product like that becomes used by tens of millions of people. And then the floodgates will open, it will cross that tipping point, and then there will be lots and lots of different products for different specialized groups. So I'm not sure if I exactly answered your question, but some thoughts.
No, you did, yeah.
Okay.
It's got to be smooth and look cool, right? That's the thing.
That is for sure. Yeah, and you saw in our prototypes, I mean, these are designed by academics, lots of wires sticking out, but it's amazing. We've had some collaborations with Nike, and it's amazing how they can take, organizations like that can take a really rough looking prototype and make it look, not lose too much of the functionality and make it look really beautiful. So I'm confident that this is accessible to that kind of process. Got a question down here and a microphone headed your way.
So looking at your design, first of all, great job. And I see the impact this can really have on, rehabilitation and a lot of other spaces. But I'm very concerned about innovations like this because what we've seen from the market is that they're usually, not so affordable. So I'm asking, because of your design process, how do you think through, making this product available to ensure equitable access to everybody?
Yes. That's a really good point. So you're saying this will be something only very rich people will have access to, basically. I think. Is that okay? I'm catching. Yeah, good. I think at the beginning, you're right that the first users of these technologies will be very wealthy. However, if we can prove that there is a strong improvement in quality of life and maybe a reduction in comorbidities, other negative health outcomes for people, we could get these kinds of devices Medicare reimbursable. When that happens, the availability increases greatly. And I think that, and I don't see another way to get this type of technology to people who really need it than to start. You got to start with. I mean, that device that you saw is probably a $300,000 device, based on the time cost of the PhD student and myself, and all that development that went into it, right? And no one can afford that. But the second one is like a $10,000 device. The second time we make that in our lab, right? And really, the core hardware is no more expensive than that of an e-scooter, right? Maybe a little less. There's less stuff there. So the actual fundamental cost of these devices is kind of low after you get past that initial development recovery phase. So I'm hopeful that in the next 10, 20 years, once we prove big improvements in quality, once things get reimbursable, once you crack a bigger market and the economies of scale kick in, we're talking about devices that are hundreds of dollars and reimbursable. That's my hope. Yeah. Yes. 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 Absolutely. Oh yeah, no, you're spot on, and that is the real challenge with fall prevention. So, there are a bunch of technologies already available that are excellent at preventing injury when you fall. For example, if you simply wear a padded underwear, that covers your greater trochanter, then you're much, much, much less likely to break your hip in a fall, which is one of the main pathways to morbidity. But that makes you look wider. It's not cool. So people won't wear it. Even like the next step of that technology that's commercially available is airbag underpants. And there really are. And actually, there's airbag, all kinds of. Have you seen the airbag helmets? You like wear this thing here and it goes over your head when you fall. And you just a tiny little microchip that is very good at detecting when you're in free fall and deploys an airbag that's very, very fast. So these technologies are there. But like you said, no one wears a thing all the time because once a year they might experience this event. So our idea here is if we can get the person to wear the thing for another reason, like every step, it helps you go faster and with less effort and reduced fatigue. Then you might have this device on also in that very rare event, and it can do something to help in the recovery. That's the path. Yeah.